And the last time we discussed the series, and we have learned and studied that we can approach the series through the partial sum. So we can set up several terms. The first few terms, like the first terms, the second terms, okay, the sum of the first term, second terms, first, second, and third, and you can move on and you can have some n term, and this means that you can set up some. This means that the sum of the sequence, which means the partial sum. Okay. Now I will write some conclusions of the series. Okay. So conclusions. So if you have a given series, and let the Sn means that this is the nth partial sum of the series. Okay. We can write the Sn as and we can have some restrictions and stop at n. So that's the meaning for partial sum. So why we need partial sum? We need to make a certain series that looks like it's going to have like infinite terms. We want to have some stop. So we can have to approach it with the partial sum. Okay. And if the sequence, of this Sn is convergent, then we can write that the limit of the sequence, the partial sum sequence, will be exist as a finite number. Okay. So this will be exist as a real number. And we can call the series of An is converge, and as a conclusion we can write A1 plus A2 plus plus An plus this will equal with S. Or we can write that the series itself of An is equal with the number S. S means that this is sum of the series. If the sequence of the partial sum is diverge, then series is divergent. So I hope you can distinguish between sequence and series. Okay? Because if the sequence looks diverge or maybe converge, maybe this series will be different, and we can see the relations later on. Okay, let me show you some practical example. If we have Sn, which is A1 plus A2 plus plus An is equal to n, sum of the series will be equal with the limit of the Sn, the partial sum. So we can take this limit and just using like the previous semester limit chapters. Okay. And we can write directly this is equal to 2 over 3. This is the first example. Second example, if you look on a series that is 1 over n and n plus 1, okay. If you treat this as a sequence, you may look like for example this one. Okay, if you treat the sequence, the sum as a sequence, you will see that if you take the limit, it will be equal to 0, right? It will be equal to 0. But if you take this as a sum and we try to modify or try to observe through different method, we may have a converged series. Okay, so if we take this, okay, let Sn equal, let's use I to difference with the questions. If we look here, let's take some few terms, okay? Let's start from 1, so 1 multiplied by 2 plus 2 multiplied by 3 plus 3 multiplied by 4 up until some n and n plus 1. And if we observe 1 over I plus 1, and using the partial fractions, we may have 1 over I minus 1 over I plus 1. I hope you still remember partial fractions. Okay. So we can take the series or the sequence here and modify its form. And by doing so, we can take the Sn and change it to our new form. Okay. With this, we can have, let's check the few terms. Okay. So this will be 1 plus, this should be minus. And then the second terms, 1 over 2 minus 1 over 3. And then the third terms, 1 over 3 minus 1 over 4. And it will goes on. And we can say that the last two terms, or the last terms, this will be plus. And if we look on the pattern, the middle part of the long range series or the sum, it will be cancelled out, right? Of course, 1 over 4 will cancel with 1 over 4 here, and something around here will be 1 over n. This will be also cancelled out. So we are going to have a new way to tell the formulations of the Sn with 1 minus 1 over n plus 1. This method, sometimes we call this method, it's called the telescoping method. Or telescoping sum. Telescoping means we are going to expand a few terms, modify a few terms, and we are going to have some cancellation at the middle. We call this kind of method as a telescoping sum. And some of the series of series or sum, they will have this property that you need to get familiar with. Okay? And maybe later on we can have more details on telescoping sum. But anyway, we have now 1 minus 1 over n plus 1. And if we take the limit, of this Sn, this will result in 1 minus 0, right? And this is equal 1. So there are differences in terms of if you treat the formula as a sequence or as a sum or series. Okay. So if we take the graph, okay, and by looking at some of the number of n, okay, so let's say this is n, let's say this is 1, this is 0. Maybe it's going down here for the an. And maybe for the Sn, it's going to have this. You can check the real number if you check one by one, and you will see that it seems that the sequence of partial sum and the sequence itself will have different results. Okay? Remember that if we are looking at the sequence of partial sums, mean that it's the sum. It's plus, 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 plus. If you are looking just a sequence, we just limit the sequence itself. And of course, it will have different values. If we look here, that Sn is going to have 1 closer to 1 and An will getting closer to 0. Okay, this property we will look more details a little bit later after maybe 1 or 2 sections. To see the relations between the convergent series and a sequence. Okay. What's the relations? Okay. Okay. The next one is it's called the geometric series. Okay, let me write geometric series. Okay. I think most of you are already familiar with the terms, but let me just remind you how we can get the partial sum of the geometric series. The geometric series itself is based on a series that is it has the differences between the terms in a ratio of r, okay, or common ratio r. We can write this as a sum and A should not be a 0. And of course, the R itself, to make our answer finite, the R should not be 1, right? Because it will be A plus A plus A. Of course, it will be having or resulting infinite, right? So we need to have our R should not be equal 1. And then if we look on the partial sum, A plus AR plus AR squared plus, and we may have the n term will be AR with power of n minus 1. Okay, now let's take this Sn and multiply with R. And let's make another line. Okay, so this will be the first line. So let's make the second line, which is R multiplied with Sn. And let me write a little bit to the right. Okay, so the first term become AR, the second term become AR squared, and so on and so forth. This will be having AR n minus 1, and it will have another term that is AR with power of n. So we have these two lines or two equations. Okay. To simplify both of this, let's subtract this 2, and we may have some cancellations in the middle. Okay, so it's all cancelled, and the rest will be A minus A R with power of n. And Sn will be A, factorize the terms A, and then over 1 minus R. Okay. And this is the general formula for the partial sum in geometric series. And remember that from the previous sections, we also mentioned that if we have R n and take the limit, and this will be closer to 0 as n getting larger, right? So if the interval of R is in between -1 and 1, okay, so the limit of the Sn, this will equal limit this, we can say that the Rn itself, this will be closer to 0, right? And thus, as a conclusion, the limit of the Sn will be A over 1 minus R. So when R is less than 1, the geoseries or geometric series is convergent, and the sum is A over 1 minus R.
Masih bisa berkuis.
Ya. And then if the R is greater or equal 1, geoseries is divergent. So if we take the example on the Zeno paradox with starting with the A equal half and the ratio is also half, we may conclude that the Zeno paradox can be completed. Okay? Like half over 1 minus half, which is 1, and which conclude our predictions because we know the distance is 1, and so thus it's true. So we can complete the problem with this approach of geometric series. So whenever you know the series is geometric and you want to know the sum, and you know the ratio is the absolute value of R is less than 1, you can just go by A over 1 minus R, and that will be the sum of the series. And another important thing on this geo series is because the form of the series is A, R, n minus 1. So if you have any random series and you want to know whether it's geometric or not, what you are going to do is you just need to check whether it has this kind of form. So, like for example, you have 2 with power of 2n and 3 with power of 1 minus n. So of course we need to check whether it has this form or not. Okay. The first thing we can do is we can take this into 4 with power of n, and we can take this 3 going down. Maybe we can check. Okay. And this 4 with power of n, we can take this and write as 4, and then multiply with 4 with n minus 1, so that it can have n minus 1 power. And then from here we can take this and write 4, and 4 with power of n minus 1 we can take with 3 at the bottom, so we can take the 4 over 3 and then with power n minus 1. So we can have this is A and this is R. And if we would like to know whether the series is diverged or converged, because R is greater than 1, the series diverge. Okay, another thing that still related to geometric is the series from 0 of x with power of n. This is where x is less than 1. So the first term, because the n started from 0, so if we take some few terms of this series, we are starting with 1, right? N plus x, n plus x squared, n plus x with cube, and plus that. So this is also geometric with a equal 1, and the ratio is x. And since the absolute value of x less than 1, okay, from the given information, so we can say that our series of x with power of n, this will be results in 1 over 1 minus x. We will go later, coming back to this series, and we can actually represent series with a functions. Okay? This is one of the examples. Okay? One of the examples. Okay. So that is all about geometric series. Now, if you remember the harmonic series, okay, if you remember harmonic series is 1 over n. Okay. So if we take this and we check a few terms, okay, and if we want to know whether it's diverged or not, or converged or not, we can check a few terms of its partial sum. Okay, so observe the partial sum. So observe the partial sum. Okay, but interestingly, what I want to show you, we just take the partial sum that is have 2 with power of n order. So we take the S2, S4, S8, S16. Okay. This is just for analysis. Okay, just for analysis. So if we take S2, this means 1 plus 1 over 2, right? Okay. S4 means 1 plus half plus 1 over 3 plus 1 over 4. Okay. Now, if we look on the number, because of 1 over 3, it seems that the number is not really that good, right? If we take this 1 over 4, it can be nicely 1 over 2, right? Okay. Now, if we recreate another partial sums to be compared with, okay, let's just change this 1 over 3 with 1 over 4, which means that if we change the 1 over 3 to 1 over 4, this means that this is greater than right? Okay. So we take this, okay? And of course, if this is 1 over 4, we can have 1 plus half, right? Or we can take this as 1 plus 2 over 2, okay? Let me just write as 1 plus 2 over 2 to see the pattern, And then we take S8. So let's write okay. Now similarly, what we are going to do, first, look here, 1 over 3, we can also exchange to 1 over 4, and same method we can compare with our sum that we recreate, and then we can compare with this, okay, and we exchange all 1 over 5, 6, 7 with 1 over 8. So this means that this is greater than 1 plus half plus 1 over 4 plus 1 over 4 plus 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8, right? Okay. So this is here. So this will be half, right? And this will be also half. So we can have 1 plus 3 over 2, okay? And it seems that if we take another one, like S16, this will also greater than 1 plus 4 over 2. And if you see in general, okay, you can say that when you have S, and you know that the terms 2 with power of n, okay, this always greater than 1 plus n over 2. Okay, it seems that from what we have observed, okay, and it seems it's true. So when the S2 with power of n getting larger, this is getting larger as the n approaching infinity, right? So which means that the series is divergent because Sn diverge. Okay, so if you think just 1 over n as a sequence, it's 0, right? Limit sequence, right? But if you look in terms of series as a sum, this will be divergent. And you still remember the improper integral, this is also divergent, right? Remember the 1 over n with power of p times series, the p times, okay? This is also divergent, right? And now, if we look at, or maybe let me take another page, another slides. Okay. So this is to show that this is the harmonic series. Okay, it's harmonic series. Harmonic series is divergent. Okay. Now there is another theorem. So if the series is convergent, then limit of the sequence is equal 0. This is what the telescoping that we have done, like in the previous page, means. So we have the sum converge, and when we look the sequence, its limit is 0. But remember, if limit 0, the series is not necessary to be converged. Okay, that's different. So we need to make sure that the series is convergent. Then we can take the limit of the sequence is 0. We cannot take reverse approach. Okay? From the previous harmonic series here, the limit of the sequence is 0, but the series is divergent. Okay? So if we know the series is converged, then the limit of the sequence is 0. Okay? Let me get you some logical proof. Just a short notes here. So if we take the Sn as A1 plus A2 plus A3 up until An, and we can take an as a difference between Sn and Sn minus 1. Okay. And let an convergent or converges. Then the sequence of the partial sum also converge. If the limit of Sn getting equal S, okay, some real number S, and n minus 1 getting infinite S and also getting infinite, right? So we also have then the limit is equal with S. So limit of the sequence is equal Sn minus Sn minus 1. This means that limit Sn minus limit Sn minus 1, which means this is resulting in S minus S and it's equal 0. So whenever you find the series is converged, and you already proved that it's converged, then the limit of the sequence of that series will be equal to 0. So, okay, just to make sure that it's clear, so the series of an means, okay, you need to have at least two sequences. Okay, the first sequence is sequence of the partial sum, right? The second is the sequence of the sequence itself. Okay. Okay, and now in the relations with this theorem, okay, this theorem says that if the series is convergent and the limit is 0, we can reverse. However, we need to say that if the limit doesn't exist or the limit is not equal 0, we can say the series will be divergent. So if we write the theorem, if limit of this sequence does not exist or limit of the sequence is not equal 0, then the series is divergent. So this is one method or one of the tools that we have in chapter 11 that is practically the easiest one. Okay, so when you have a formula of this series, you can check directly the limit. If you get the limit is not equal 0 or maybe it doesn't exist, you can directly answer it's divergent. The series divergent. But if you check the limit is 0, it means we are not sure yet. We cannot make it into converge or diverge. Okay? We need to take another tools or another method to check. Okay, some property, property of convergent series. Okay. So if the series are converged, so does the where C is a constant, and also let me just write here, we can take several property. Then minus. Or maybe let me write that this means this is converge. This is also converge. Okay. Which means that if you can manipulate the whole series here and separate it into two series, maybe it will help you. So whenever you separate this, maybe one of them is diverged. If diverged, then it means that the whole thing will be diverged. But if it is converged, then you need to make sure the other one converged or not. And sometimes the questions or the problems, it doesn't need to really, you need to find the exact value. It's just asking whether it's diverged or converged. Which means that it's not necessary to find the value, but you can think whether it's converged or diverged. And there are several methods, at least 6 to 7 more methods to check whether the series is diverged or converged. So this is among the first first method. It's called the divergence test. And this is called the divergence test. Okay, I think we can just stop until here, okay? And we can continue the next sections, the integral test on Monday.